Okay, I guess we're live. Uh, Thank you. Asher, can you hear me? So thank you very much, guys, for attending our second major event of One Quantum Philippines. My name is Bobby Corpus. I am currently the president of One Quantum Philippines. So let me introduce you first to who we are as One Quantum Philippines. So we are a chapter of One Quantum. It's a global community on quantum technologies. Um, we started here in the Philippines as Quantum Computing Philippines way back in 2017. Back then, we were struggling to penetrate into the awareness of Filipinos, since, for one thing, this is not an easy subject. Fortunately, we have been noticed and absorbed by One Quantum Global, whom we share the same mission. We want to increase the awareness of Filipinos to quantum computing to make Philippines a quantum-ready country, to make it accessible to anyone interested, and most importantly, to introduce it as early as possible into the children's education. So quantum computing is a paradigm shift away from the way we do computing today. So we have to wire our minds to the way things are done in quantum computing. And what better way than to introduce it as early as possible in the education to make the kids quantum native. So tonight, we are very fortunate to have a special guest. His name is Dr. Harny Wang. So Harny's given name is Quanlong, which is obviously a quantum native name. Harny got his first PhD in mathematics from the Chinese Academy of Sciences in 2004 and finished his second PhD in computer science at Oxford University in 2018. Since then, he has been a postdoc at Oxford University and Cambridge Quantum, respectively. He is now a senior research fellow at Cambridge Quantum slash Quantinuum. His research mainly focuses on the theory and applications of ZX calculus, which is a graphical language for quantum computing. Ladies and gentlemen, please welcome Dr. Harny Wang to introduce us to ZX calculus. Uh, the floor is now yours, Dr. Harny. Thank you.
Thank you very much, Bobby. Thank you for having me here. So today I will give a basic introduction to ZX calculus. Sorry, why I can't. Okay. So basically, I will first talk about the general process theory as a background, and then I will talk about the theory of the ZX calculus, and then show how to apply ZX calculus to different fields. So first, so how do we think about everything in the world? So according to Whitehead, which is a famous philosopher, and I think also many other philosophers, that everything in the world can be seen as a process, no matter physical process or mental process. So what is a process? So process can be seen, each process can be seen as a change from something typed as A to something typed as B. For example, so if we have some potatoes, raw potatoes, and we cook them to get roasted potatoes, and then this can be seen as a process. So we can write them in a diagram. So which means the A is the raw potato, and F is cooked. So the type is roasted potato. So you can see we can write them as a diagram. We read from top to bottom. And so if two processes, they happen sequentially, like first happen G and then happen F, and then diagrammatically we can connect these two processes, connect them as a whole process. So we got the diagram for the sequentially happen processes, and similarly, if two processes happen simultaneously, then we put them in parallel, like F and G, right? This is a way to represent two processes which happened at the same time. But then how about then there is a problem if we do this kind of representation of diagram of processes. So first, since we put two simultaneously happening processes in parallel in a plane, so one diagram has to be on the left and the other one has to be on the right, but actually they happen simultaneously. So there is this notation has a kind of artificial asymmetry. So to break this artificial asymmetry, we want to have a nice way to convert the from the left to right, the left to right FG into the GF, and if they are swapped, right? We want to have a nice way to do this. So we need that means we need a symmetry process from AB, which is a swap. That means you can such that you can swap the position. You can swap the position. You can slide across, slide the crossing, and then get this one. So basically, they are the same. Essentially the same up to this swap, right? So of course we want to this swap to be how to say, to be self in a kind. The inverse of the swap is still a swap. So we want to have this property. So once we have this symmetry diagram, then we can break this kind of artificial asymmetry. Also, if someday, because we write down in a paper or in a plan, and then if someday they read the diagram from the opposite side, like vertically opposite side, then the diagram from A to B then become the box become this a flipped version, right? So this is also a kind of how to say, a kind of artificial asymmetry. So to break down this up down asymmetry, so we also need a nice way to convert these two diagrams to each other, right? So how to realize this? So we can use the cap and the cup for any cap and a cup. So if we introduce the cap and a cup structure, then that means you can look you can slide the F box from A to B. You can slide it here, either here or there. Then you get this B to A F with a snake. So we want to ask the cap and a cup. They satisfy this property. They are symmetric here, and also they satisfy this snake equation. That means if you connect this cap and a cup, then you can do yanking. Okay, then actually that's the backbone. That's the backbone of the what we call categorical quantum mechanics, which was initiated by Samson Abramsky and Bob Cook, right? So this is basically mathematically, this structure of the process theory is called compact closed category. So this is a backbone of the what we call CQM, categorical quantum mechanics. So, but that's from a general process. For general process, we want to have some to make them look nicely. So we can have this kind of theory, but you can, as you can see, this is not just some boxes about some boxes, right? The processes. It's not. It's very good, but it's if we want to apply process theory to solve some particular problem, like quantum circuit optimization or quantum entanglement and classification, whatever, then we need a fine-grained version of process theory. That means all the boxes. What we need to look into inside of the boxes. What is inside the boxes? So typically we this kind of there could be quite a few ways to make a fine-grained version of process theory. A typical example is what we are going to talk about today is the ZX calculus, which is introduced by Bob Cook and Ross Duncan in a paper in 2000, published in 2008. So now we will from now on we will focus on this ZX calculus as a fine-grained version of categorical quantum mechanics. So basically, how could we build up the box with some details? So basically, the idea is to use spiders. So I will give some rough idea on what kind of these spiders are, and then I will talk about them formally. So basically, so the spiders, so we use two types of spiders. One is red, one is green, and with some labels, some numbers as a label, and we use them as a basic building blocks. It's like doing a legal way. That means we compose these spiders either by connecting the legs or put them in parallel. This is exactly what we did for playing Legos. So we denote this operation. We can by the connection by circle and in parallel operation by a tensor, like a tensor product symbol. So what do once you build this box with spiders, what do you do? So what the behaviors of these spiders? So it's very intuitively. So basically, if they are in the same color, if the two spiders are in same color, like for example, if they're both in green, and if they are connected, then they just merge. And with the parameters, they just summed together. So the same color, if for red, is also if they meet together, they connected and then they merge. So I will show the formula. Just don't take these kind of things too seriously. It's just some a kind of cartoon styles made by my daughter. So if these spiders, they are in different color and they connected with at least two wires, like here, then they hate each other. They don't like before. They fuse, that means they love each other. For now, if they're in different color, they hate each other and they will get disconnected. So that's the basic behavior of these spiders. And so formally, what are the spiders? What does these spiders mean? So basically, it is like this. It's a parameterized diagram. So with two colors, green and here I draw it as a pink. So with some parameter, it's alpha, could be any real numbers, and we have some inputs and outputs, and m could be zero. So then you just like I said, you just connect them with the wires connected, or just put them in parallel, and then in this way you can compose any diagrams with these two generators. But mathematically, so how could so we should have some rules, right, to guide their behaviors. To guide them behaviors, like here we put some like copy rules, or this kind of color, or this kind of we call bialgebra rules anyway. So so here the information is how you can use some rules, some these equalities, we call them rules. You can use some rules to guide the behavior of these spiders when they you can see when they glue together. So the problem is how I will show by some example on how to use them, but for now we just want to we just need to know that you add some rules. So first you have some generators, green and red spider, you put them together, and then to have some big diagrams, and you have some rules to change them. The problem is how to ensure that these rules they are added by some white men, and not randomly composed by some like monkeys anyway. So basically it is how could we know whether there is any conflict inside this reasoning diagrammatic system. How do we know that? So to know this, we need to give the semantics to this diagram. So actually the semantics for this diagram is there is a very standard one. So that means you give diagrams matrix meaning. So that means each diagrams, like the green spider, they just corresponding to this diagram, this matrix, which means on the top is the first element is 1, and all the other elements are 0 except this one in the corner, which is e to I alpha. Alpha is the same as this parameter alpha, and so you have 2 to n. I think you have 2 to m columns and 2 to m rows. Yeah, that's how it related to n and m. So for the pink spider, it's just use another basis. So for convenience, I didn't use the matrix form because that would be very big. So I just use the direct symbol. So basically use the another basis, the Fourier basis is the plus and the minus. Okay, and then once we have the interpretation for the two diagrams, for the two generators, and then for all the other because matrices has also has multiplication and tensor products. So the tensor product of diagrams is interpreted as the tensor product of corresponding matrices, and the sequential composition of the diagrams is corresponding to the multiplication of the corresponding matrices. So that's I think that's quite a direct way to interpret these diagrams as matrices. That's also how you related this. We will see later how this diagram is related to the quantum computing. So so once we have this matrix interpretation, then we can check the whether there is any contradictions. That means that's what we call soundness. So we just need to check that, for example, here, if you have some rules, if you add any rules, you need to make sure if you interpret the diagram into matrices, they should be also equal. If they are equal in diagram, and they should also equal in their interpretation in matrices. So that's how you check the soundness for this added rules. So so from the beginning, as Bob and Ross introduced the ZS calculus, they have checked ZS calculus is sound. So it's fine. There's another important property for this diagrammatic system. That means is ZS calculus expressive enough? That means for any matrix, or linear map of size 2 to m times 2 to m, because we mainly consider the qubits case. So whether you can represent any matrix of that size in whether you can represent them or encode them, the matrices, into a diagram. So in other words, that means whether ZS calculus is universal, we call it universal. And also from the beginning, we know that the ZS calculus is universal. So so the last question, the last important property about ZX is completeness. So that means is ZX calculus is powerful enough? Because for now we don't have any matrix calculation. We just have diagrams transformation, right? So is this in this diagrammatic system? Is it powerful as the matrices, right? So so this if yes is the same as the same power as the matrices, then we call it complete. So actually, so how about the completeness of the S calculus? So actually, this is sorry, I got some typo. It's it's most yeah, and it's the most trickiest part. So it's not trivial. So basically, the first completeness result come from Minimum-Bacon's about the completeness of a stabilizer quantum mechanics, which basically means the angles, the parameters of the spiders are multiple of pi/2. And then the next one, which is important progress for the completeness of ZS calculus, is made by a French team. These authors, they have completeness proof for the graphical quantum mechanics, which means the parameters of the spiders, they are multiple pi/4. This very this is a very important one. And then based on these results and the graphical completeness, we have the first universal. That means for all the parameters, completeness for ZX. That's, I think the first version was finished in 2017, and then we incorporated this results in a paper with Amar, which is published in 2018. So basically, the key idea for used here for the first version of the completeness is to to use translation from another calculus called z-dot calculus, which is already proved to be by Ahmad to be complete, universally complete. And then after that, there are several more universal completeness results from using different methods or from different perspectives. So it's mainly from the French team, and they use the translation, or they use I will introduce later the squad PLU, which is important, based also based on our paper, another paper. And also there is a very simple where there is a normal form one, so it's not using any translation. So anyways, that means the non-trivial part for the theoretical aspect of the ZX calculus is the completeness. But for this qubit case, we have solved this problem anyway. So what is the loose looks like if it is complete? That means the ZX calculus has the same computational power as the matrix. It's actually there is a very simple table loose set for ZX, which is complete. That means you just need like the fusion rule of the green spider, which you can see here. Once they're connected, at least one, while at least one lacks, then they are just fused together, just fused with the parameters just summed up. And with this rule, this is just if there is circle, it just if the circle, that means the parameter is 0. So if the parameter is 0 as one input and one output, then it's exactly the same as identity. So this means just these two scalar makes an empty square. Empty square represents the scalar 1, just scalar 1. And this means okay, the red dot can be copied by the green, by the green spider. And here, this is what we call bialgebra rule. So basically, that means you can break this square. This is a square. It's closed, right? You can break them. And this is how do you? This is about how do you decompose the Harman gate. And use the Harman gate, you can also change the colors of the green and red spider. And finally, the most complicated. When I say complicated, because we didn't show the beta, the values of beta here is complicated, but the rule itself is just about how do you change the colors? How do you change the colors from green, red, green to red, green, red? How do you change the colors once oral decomposition of a unitary is given? So basically, that makes all the complete set of rules for ZX. Of course, you can have another. We can have another set of rules, but they are equivalent in the sense that they all make ZX complete. Okay, so you can see that is basically how do you what basically ZX calculus is. But we should bear in mind that having completeness, not the end of ZX calculus. It's basically is the right beginning of ZX calculus. That means based on this completeness result, and then you can apply ZX calculus. Almost you can apply everywhere. So I will show how to apply ZX through some examples. But first, we want to know the idea on how to use the ZX calculus. So basically, so when you want to use the ZX calculus, the idea is quite similar to how to play with the Go game. So the Go game, you can see, as you can see from this picture. So in a Go game, if you don't care about any win, you don't care, then it doesn't matter. You don't need to know any rules. You don't need to learn anything, right? You just put the stones on the board, and right, just put stones on the board. But if you want to win, when you play the Go game, so you need very good strategies, right? So similarly, when you using ZX calculus, so if you don't want to use it to solve any problem, just play it for fun, then you can just play with the diagrams by randomly. You can use the rules and do some rewriting. So rewriting means you just replace a part of the diagram with another diagram, so according to some rule. So I will show some examples later. So, but if you want to use it to solve some problem seriously, and then you also need some very good strategies. So you need to decide what kind of rules you want to choose, and so in what kind of order you use them. So now I want to give some example for the application of ZX calculus, especially in quantum circuit optimization. So to use ZX calculus for quantum circuits, so the first thing you need to do is to encode the quantum circuits, the quantum gates into ZX diagrams. So fortunately, there is a very direct way, very easy way to translate the quantum circuits into ZX calculus. So you can see here the Harny can just the Harny gate is just in ZX calculus. We also have although at the beginning we didn't use it as a generator, but we can have it we can define it in terms of the green and the red phases. But here we usually use a box, yellow box for the represent the Harny box, and the S gate is just the pi by 2 green phase. Green spider with one input and one output, and the S dagger gate is just minus pi by 2, and for T gate is just pi by 4. T dagger gate is minus pi by 4. The usual Z gate is green pi. So the S gate is just the pink or red pi, and the control Z is just just 2 green with the Harny in the middle. So, and the C0 gate is just 2 spiders, is red and green. They are connected. So you can see it's very easy to translate and quantum gates into ZX diagrams. Okay, so let's see. So how could ZX works for the quantum circuits, right? So here let's look at the a non-trivial example. So if we have a quantum circuit like this, a quantum circuit like this. So if we, and this is this quantum circuits made of some Toffler gates, right? So if we represent the Toffler gates in terms of Clifford plus T set gates, and so how do we reduce the T count, which is the number of T gates of this circuit, to make it as few, the number of T gates as few as possible, but don't change the circuit itself. That means you don't change the corresponding matrix of the circuit. So how do we do that? Using ZS calculus. So here, so we can do in this way. So first, you write them in a quantum circuit. That's a standard, which has seven. Usually, seven. You can check any textbook. You can find the quantum circuit for the Toffler gate. Also, is called CCZ gate. Sorry, it's CCZ gate, not Toffler gate. Sorry, it's CCZ gate. Toffler gate is with conjugated by Harny gate. So for the CCZ gate, you have you can find the quantum circuit for it, and you encode it in this diagram, then it looks like this. So again, if you count this circuit for the CCZ, you find there are 1, 2, 3, 4, 5, 6, 7. That's seven Clifford. There are 7 T gates, right? 7 T gates. So that means T count is 7. So at the beginning we have 4 CCZ gates. Like here we have 4. 1, 2, 3, 4. We have 4 T gates. So how could we? Then that means the T count of the circuit of this circuit is 28, right? It's 28. So how do we reduce them? So we need to do some rewriting. We need to do some rewriting when we use ZS calculus. So how do we do rewriting? Rewrite means, so here, for example, here, this diagram has two green nodes, and they're connected, and then we can use the fusion rule to put them together, right? That's the fusion rule. And then we also use the fusion rule in another way. That means we can split, but they're still connected here, right? And then we can slide, because in a diagram, the connection, the location doesn't matter, and the connection matters. So we can move this alpha, from here to here. We just move it, and then we use the fusion rule opposite in another way. That means we split it. Then if you remember, this is what we have at the left of the bialgebra rule, and then that means we can use the bialgebra rule to get this diagram. We replace this part with this part, and then we write them in a nice way. Then we get this. So also you can see here, if we have this diagram, then we can use I didn't write down here. We can use the hop flow. That means two different colors, red and green, pink and green, they are connected by 2 wires, and then they actually can get disconnected. So we use them in the opposite way. So that means we can create this diagram, and then fusion them, then split them into these two, and then you get this. Because this part is just this, as we have just demonstrated. So that means here, if you have alpha on the right at the bottom, and there is a C0 gate, and then you can change the order. But once you change the order, you then C naught become here, but you pay the price that you got a more complicated one, this phase gadget. We call phase gadget. Similarly, if here, if alpha is on the right, on the left, and C naught on the right, then you can also change the order and you get this one. You get this one. Get this one. And if you have a C naught and a phase gadget as what we just obtained, then they can also swapped, but at the price you get another a kind of more complicated phase gadget. So that's the way we can change. Basically, how do you tell you how do you use the C naught and swap with the diagrams like this, Okay, so in general, we call this kind of thing. You have some green, and they all connect to some pink, and with some, and then with some with one connection with another green node. We call this thing phase gadget. So phase gadget has a very nice property that they can fuse two phase gadget with the same shape, and they behave like a spider. They can just fuse together to get the parameters summed up. Okay, so basically, so then for one CCZ gate, use the tricks I just showed. Use the C naught and change it with the green phase. Then we can first move this pi by 4 to the left, and then you use those tricks, and then you get this one. You put them together. You put all the C naught together, and then you want to use addition. You fuse them and use some half floor to cancel out this like two C naughts, and then finally you will get some get a diagram with this. This kind of thing we all call phase gadget. This is just have one. This have 2 legs. This have 3 legs. So we have this phase gadget. So now you can see. Basically, to summarize, for this CCZ gate, if we use cliff plus T to represent them, and use diagrammatic rewriting, then we finally get this. So that means if you put all the CCZ together, then we get this one. So so if you count them, you can see the T count now becomes just 8. Before it's 28. Now it's just 8. So if you so I think I don't have enough. Maybe I have not enough time. So maybe I just show quickly. If you have some more complicated rules like this is what we call spider nest identities. That means you put this phase gadget together, and then magically they are vanished. They are just identities, and or there are more complicated ones. So they were vanished. So basically, that means if we can find some identities, some equalities of these diagrams, and which just involve those tickets, or Clifford plus tickets, and then because it become identity, that means if you have half of them, if half of them they are how to say, half the phase gadget, more than half of the phase gadget already existed in the circuit. If we apply them, then you get then you will get the T count reduction. You will get T count reduction. So anyway, if you apply this kind of thing to benchmark it, this kind of thing to benchmark the circuits like this one, then you, as we did in this paper, then you will get quite some very good results. That means you will get some very good. You can reduce quite a lot T gates in the benchmark circuit in comparing to other methods. And also, if we do it, here we use some probabilistic method anyway. That means you apply the identities in a maybe a random way. Then you will get for much more benchmark circuits, you will have better results than the previous best one. Especially for here, like here we have for this very big circuit, which has like 1 million at the beginning, has 1 million like tickets. Then you can reduce them. A lot. So that's the showing case of how to use ZX to reduce quantum circuits. But actually, you can have more applications like for the BB84 and ACT91 quantum protocol. So if you look at the beginning of the description of the protocol, it's just lots of blah blah blah, right? But if you write them, if you represent them by ZX diagram, then essentially they just means, oh, if you use the same basis, then they just either get disconnected, connected. Either they get a identity wire or banded identity wire. But if you choose complementary basis, then they will get disconnected. That's the core thing of the quantum key distribution protocols. So also there are some other application like if we extend the ZX generator a little bit, then we can do even do something more, like we can do Gaussian elimination in ZX. So like that's what we did recently. We implemented and represented and implemented the any matrix of size 2 to m times 2 to n. We can represent them by diagrams, and so we can also do the Gaussian elimination. So here is some diagrams represented, some which represent some matrices. These diagrams are automatically generated by a software called DiskPy. And also, actually, you can also differentiate and integrate ZX diagrams, the given ZX diagrams. So, for example, here, if you have parameters, if you want to calculate the derivation of the diagram for this parameter theta, so you will, from this diagram, after differentiation, you will get this diagram. So that means you also have a way to differentiate, also integrate these diagrams. This is also what we did very recently. And actually, we are going to, we have a paper which accepted to QPL this year, so which will happen next week. So in this work, what we do is to sum and exponentiate some any Hamiltonians in ZX, and also we can give a diagrammatic proof for linear linearity of the Schrodinger equation, which is shown by this diagram. And so so you can, as you can see, actually you can use ZX for a lot of things, from quantum circuits and to this quantum dynamics, a lot of things. So if you want to try, what you can do with ZX, I think there's lots of things you can try. Basically, you can do quantum circuit optimization, and also you can do, as we have a way to differentiate and integrate these diagrams. So that means you can try something on quantum machine learning, especially if you want to analyze the Baron-Platter phenomenon, which is a very important property for quantum machine learning algorithms, right? And also you can try something in quantum chemistry, like Hamiltonian simulation and diagrammatic properties of Hamiltonians. We can represent any of them. And if you are ambitious enough, then you can also try classical machine learning. So for example, how to have rewritable neural networks, which could lead to interpretable machine learning algorithm. I think that is a bigger goal of classical machine learning, right? Yeah, I think that's what kind of things you can try. So if you are interested, yeah. So that's all. Thank you very much.
Thank you very much, Dr. Harny. We have some questions here. I'd like to read out some of them. So there's a question here. What's the best resource for continuing with ZX calculus? Is there a diagram cheat sheet?
You mean the resource, right?
Yeah, resources.
So we have we have a website which called zscalculus.com.
Okay.
I think you have yeah, then you basically have everything there.
Okay. Yes, calculus.com.
Yeah, just zscalculus.com.
Yes, so here's another question. Is ZX calculus almost exclusively used for quantum circuit optimization?
Yeah, I mean, I think for now, a lot of applications of ZX calculus is about quantum circuit optimization. But as I have shown, you can also, as I have shown, you can do something in like quantum machine learning, like the Baron-Platter phenomena and analyzing and Hamiltonian thing. That's what we did very recently. But actually, before there's also something else, like the encoding, like the how to say the quantum error correction, and of course quantum protocols. I think they're quite like yeah, and so and surface codes. That's I think a lot of things you can try. I mean, if you look at the website I just mentioned, like zscalculus.com, there are all of the papers related to ZX listed in that website.
Okay. So another question here is ZX calculus the logic behind the continuum circuit optimization library?
Yeah, as far as I know, yeah, there's quite a lot ZX technologies used in the ticket software.
Okay. Another question is, I can draw a quantum circuit with matplotlib, and I can convert it to LaTeX. and so forth. Is there a tool to render a circuit in ZX calculus?
You mean the so you mean the what is what comes in? Do you mean that actually there are some software which you can draw diagrams, draw ZX diagrams, which is called DigZit, and also there are some automatic software which you can do automatic reasoning, which is called, I think, quite there are a few of them. One is called PyZix, PyZix, PYZX, PyZix.
PYZX. Okay.
Yeah, PyZix. I think it's developed by Alex Kissinger and John Van Wetering. And also there are some other tools like I think we can now also use DiskPy, but I think it's still under developing. Yeah.
Yeah. So I have a question here. So ZX calculus is was created. Is it created so that we can encode our, so which means that it's a way for it to automatically solve problems and reduce them into something like so it's like can you make it into like a computer algebra system where I mean something like that? Is that how we can also use ZX calculus?
Yeah, I mean, as I mentioned, this software like physics, you can you can do a lot. Like I think this year they have even in Oxford University, and they have I think they have a course called like ZX software, and they just teach you how to reasoning automatically with this diagram.
Okay, so yeah, because with the rules of ZX calculus, I was thinking that correct me if I'm wrong. I was thinking we can probably use some genetic algorithms, or what you call this genetic programming, in order to come up with some optimized circuits, right? Is that something that you think will can be used using ZX calculus?
Maybe I'm not quite sure, but I know there are something. Yeah, I know that there are some work like they use different strategy, like but different how to say, different software to different algorithm to reasoning about ZX diagrams. Like for example, like they have you heard about the Wolfram framework?
Yeah, Wolfram. Yeah.
Yeah. They use some they use hypergraph. They use hypergraph, but they apply them to ZX calculus, and they also get some good results, I think. Yeah, so quite probably if you try some algorithms like you said.
Okay. I think we have one final question here. It says here, I might have missed it, but are nonlinear functions implementable in ZX calculus? I'm asking because non-linearities play a big role in deep learning.
Yeah, that's a very good question. Actually, we thought about it in this question. So basically, as far as I know, there's one because one typical way to use like nonlinear function in machine learning is to apply apply the nonlinear function element wisely to a vector, right, or matrix. So in this way, so we have a normal form. We have a normal form for any in ZX. If you we call algebra ZX. We have a normal form to encode any vector or any matrix in ZX diagram, and in this way you can just, if you apply a nonlinear function, you can just apply to the to different parameters in the diagram. So that's the way you can do. If you apply them, if the nonlinear function is apply the element wisely. Yeah.
Okay, so I guess that's it. I didn't find any more questions. So I was actually talking to one of my our members here, Brian. His name is Brian Cyclewax, and I was asking him, so how do you think we can use the X calculus, like for example, to demonstrate how to solve the Bernstein-Vazirani problem? So is that something which we can do?
Sorry, what was the problem?
Yeah, so there's this algorithm called the Bernstein-Vazirani in quantum computing. So I was asking if we can use this calculus in order to simplify that big equation into the actual answer.
Yeah, I think it's quite possible. So if you first encode, like we encode protocol, if you encode the algorithm in this diagram, then quite probably you will find a simplification.
So thank you very much, Dr. Harny, for lending us your very precious time in teaching us about ZX calculus. So, well, for our attendees, thank you so much. So One Quantum Philippines also has so these are one of our events, and we also have a regular lecture series on the basics of quantum computing. So in there, we will teach you the basic algorithms like Shor's algorithm, Grover, and also we will show how quantum computing is used to solve industrial problems. So thank you very much, Dr. Harny. Do you have any last things to tell the group?
I just want to say thank you for inviting me. Thank you, Bobby, and thank you, Brian. Yeah, thank you, everyone.
Thank you. You're welcome. So thank you, guys, and goodbye. Thank you.